thank you, Dr. Roberts, for that introduction. Um, so, brief background of the CLEAN project. CLEAN stands for carbonless electric, or sorry, carbonless emissions in aviation. A CLEAN engine is a solid oxide fuel cell hybrid system. It's a fully mixed turbofan, and the goal is to have zero emissions other than water and nitrogen. So we're using ammonia as the fuel for both the turbine and the SOFCs. Our system has an ultra high bypass ratio. Our BPR is about 30, whereas the LEAP 1B has a BPR of 9. And we have such a high BPR because less flow is required to go through the core and the turbine, since the SOFCs help produce additional propulsive power. Some of the struggles that we're having in our system is that the system itself has a lower energy density, as well as ammonia fuel has a lower energy density than jet fuel. So this, coupled with the fact that most of our thrust is coming from the fan alone, results in fan inefficiencies having a much more pronounced effect, much more detrimental effect compared to traditional engines. So it's really key for this project to be commercially viable to have a very efficient fan. And I'm using two methods to optimize the fan. The first method is particle swarm optimization. It's a stochastic optimization technique based on the movement of swarm organisms, such as like a flock of birds or a school of fish moving around in space. Each particle represents a potential design within the total space. It moves according to its own personal knowledge of where it's been and what the best point that it has found to be, as well as it's influenced by the knowledge and the movement of its neighbors around it. So the net effect of this is that the swarm as a whole tends to move towards the best or most optimal solution. Some of the strengths with PSO is that it does best with unconstrained or continuous variable problems. It especially performs well on small to medium-sized problems. Generally, it can require fewer objective function evaluations for it to find the best result, and it has a really good balance between global searchability and local searchability. Though one of the downsides is it can get caught up in local minima, as we can see in the graphic on the right, even though the swarm as a whole tends to move towards the best solution in there. There are a few outliers that get trapped in the local minima around the global minimum. Additionally, it struggles with problems with a lot of constraints or discrete variable problems, and it can scale poorly with larger scaled problems. This brings me to my second optimization method, the genetic algorithm. This one is also a stochastic optimization technique. It's inspired by the phenomenon of natural selection in evolution. Each individual, again representing a point in the design space, has a genome, and more fit individuals, so individuals that are more highly optimized, are more likely to reproduce than less fit individuals. And those children that result from the reproduction have modified genomes. They can either be modified through crossover through one of the parents or the other parent, or through random mutation of a specific gene. And the combined result of this is that the population as a whole tends to evolve itself towards the best solution within that space. One of the strengths with genetic algorithm is where particle swarm struggles, genetic algorithm typically performs better with overly constrained or discrete variable problems, meaning that it can be more robust for certain complex applications. Additionally, it can exhibit faster convergence than particle swarm, but at the downside of its tendency to lose population diversity rather quickly. So what will happen is once it finds a good design, the entire population will move towards that point, and it will sort of get itself stuck in that niche, even if better solutions exists. Additionally, it has a pretty poor local searchability, which is also due to that tendency to lose its population diversity. The reason I picked these two algorithms to compare against each other is they're both stochastic techniques, and they're both inspired by natural phenomenon. So PSO is inspired by the movement of a population and genetic algorithm is inspired by the evolution of a certain population. So they're pretty similar techniques. They have similar requirements for their setup, and it's a similar process to set them up. So I was particularly interested in comparing these two, comparing their behaviors. So the way I'm going about implementing these optimization techniques is I'm doing all of the optimization in MATLAB using the global optimization toolbox's built-in set of algorithms. This toolbox has other algorithms as well, such as multi-surge, surrogate optimization, or simulated annealing. But for this study, I'm only considering PSO and GA. And the baseline fan design to be optimized and all of the resulting simulations are performed within AxSTREAM. I'm using their mean line solver. So all of the calculations are performed at the mean of the length of the blade, and results for the hub and the tip are extrapolated using free vortex radial equilibrium. And then profile losses across the blade are being accounted for with the Liveland model with shock included. And these profile losses can account for us being in the transonic region, particularly at that tip. You can start to get trans or supersonic speeds, and this loss model can take that into account. The biggest benefit with using the AxSTREAM mean line solver with this is it takes a lot less time than running something equivalent in any other CFD software. I found that it takes about 15 to 20 seconds to run a single fan simulation, where if you're using something like ANSYS, even in 2D, it can take maybe on the scale of 1 hour to a few hours to run one simulation. So I'm able to run all of these simulations very, very quickly, which means that I'm able to do a lot of optimization in a shorter amount of time. So here's a more detailed flow chart of my optimization process. So you get the laser pointer. So we start up here with the baseline design within AxSTREAM in this blue box. And then we move on to the orange box in MATLAB, where we either set up if we want a particle swarm or genetic algorithm optimization scheme. Here we set up the size, which is how many particles or how many individuals are to be evaluated. We set up the length, which is how many generations or how many iterations of optimization are carried out. Here we also set up the bounds of the problem, so the upper and the lower bounds of the design space, and any constraints that we want to apply as well. So if we're targeting a specific thrust or specific power consumption, we set that up here as well. That's everything that has to be set up on the user end. And then we move into this black dotted box here, which this is the main optimization loop. Within that, the initial population is created, and then that gets moved over into AxSTREAM, where the fan simulations are run for every one of those particles or every one of those individuals. That data is then collected from AxSTREAM, moved back into MATLAB to run a blade refinement script. With this just iteratively runs AxSTREAM and runs that refinement script in an attempt to minimize the incidence angles and deviation angles from the blade, just to try to get as smooth as a flow path as possible. So once that's done, the final data is sent over to another script, the thrust calculation script, which this takes in parameters from our steady state model, the turbine exit properties and the ambient pressure as well, and runs it through the mixing chamber equations. So we're able to get a calculated thrust value that the specific fan produces. From there, we can apply the constraints. Again, if we're trying to match a certain thrust or stand or a certain power, these are applied as well. The fitness is evaluated for each one of the individuals, and until it reaches its end, a new population is generated. And the way that the population is generated will vary between PSO or GA. And this whole loop is repeated again until the end of the run is reached, and then you end up with the optimized design in AxSTREAM. Then you can go in and do more analysis and stuff on that. So this table on the right is our list of design requirements for the cruise conditions. This is all taken from our steady state model from EASE. The design variables I'm considering in this study are the shaft speed. I allowed it to vary from 75% to 200% of the baseline design shaft speed, and the number of rotor blades and the number of stator blades, which I allowed to vary from 7 to 30 blades total. I have constrained the thrust to be within plus or minus 10% of the nominal thrust value of 12.7 kilonewtons, and I've constrained the power to be less than or equal to the 3,300 kilowatts of total power available. To enforce these constraints, a static penalty factor is applied, and I've done 3 sets of cases or scenarios where a differing level of penalty factor is applied. The first one is apply no penalty factor. So if the constraint's not met, nothing happens. Then I've applied a small penalty factor of 0.1 and a large penalty factor of 0.25 if those constraints are met. And this penalty factor is just a flat rate static value that is added to the fitness value for each constraint that is violated. And what this effectively does is say that that design is that much less efficient. So for example, for the small penalty factor of 0.1, if we have a 90% efficient design that consumes too much power, the penalty factor would make that design be seen as 80% efficient as the optimizer sees it. So then the optimizer tends to avoid those regions and pursues more favorable regions that do meet the constraints. I'm also studying the effects of size, which is the number of individuals in the population, and the length, which is the number of generations that those populations are allowed to evolve or move within. I have a set of 10 individuals, which I run for 10 generations and 25 generations. Then I have another set with 25 individuals that I run for 25 and then 50 generations. And again, I'm changing these things to try to observe the algorithm's behaviors under different sets of scenarios. Lastly, I have 2 methods in which I'm calculating the efficiency. The first is the propulsive efficiency, which is a comparison of the engine's exhaust velocity compared to the flight velocity of the aircraft. And this is calculated within MATLAB. The thrust calculation script, in addition to giving us the thrust value, it also gives us the exhaust velocity value, which is how I'm able to calculate the propulsive efficiency. And the second method of efficiency is the adiabatic total efficiency. This is called FTT within AxSTREAM, and this is calculated directly within AxSTREAM. So I'm able to just pull this value straight from the resulting files. And this is a measure of the ideal enthalpy rise over the actual enthalpy difference across the machine. So I've designed the baseline fan for the cruise conditions using the previously shown table from our steady state model. I was able to put the set of boundary conditions and constraints into AxSTREAM and generate this preliminary design space seen over here on the right. And each one of these points represents a potential design that could meet the boundary conditions and constraints that I've provided. For this baseline design, I've limited it to only have the amount of power available from the SOFCs. And I did this because I want this baseline to also serve as the baseline for a counter-rotating fan version, where one stage is powered by the SOFCs and the second stage is powered by the gas turbine. And I would like this to be just a common baseline for both, so I can try to get a direct comparison between the two. So here's an image of the baseline design. This was rendered within AxSTREAM in its 3D viewer. And over here on the right is a table of some of its performance metrics. So as to be expected, since it has such a limited power that it is available to it, it only makes about 4 kilonewtons thrust, which is way under what is required. Additionally, the pressure ratio, the total pressure ratio, PTR, is pretty low, but that's to be expected since so little work is being done on the flow. As for efficiency, we see it has a moderate total efficiency of about 89%, but it does really well on propulsive efficiency at about 95.7%. And that's due to, since so little work is being put into the flow, the exhaust velocity is very slow and it's almost matching the ambient velocity. So it's to be expected that the results from the optimization enforcing the constraint of the thrust, that this propulsive efficiency would be a bit lower than the baseline actually. So this slide is the results from my optimization, and I know it's a big table of numbers and I don't want to get bogged down in the specifics, but I more want to examine the general behavior of the algorithm. So any text in the green signifies that constraint was met, and any text in the red means that the constraint was not met. So the first thing of note is that for the particle swarm, all of these runs across these different scenarios, it actually ends up at the same point every single time. So for the 10 by 10, where it's 10 particles ran for 10 generations, it ends up at the same point as the 25 by 50 run, where it has a lot more time and a lot more available particles to search out that space. And this really shows its great searchability. So even with the smallest population size and the smallest amount of length, it's still able to find the most efficient design as it was with a much larger population for a lot longer of time. Comparing that to the genetic algorithm, we don't quite observe the same searchability in there. They vary slightly between the runs, and an additional thing to note is that in these set of runs, the GA performed a little bit lower efficiency than the designs that were found by the particle swarm. All of these particle swarms were about 99% efficiency, whereas in the GA we can say this is 98.8, 98.9, 98.8. So it's ever so slightly less efficient than the ones found by the particle swarm. And we can observe that here in this right columns, or in these two right columns, where both of the constraints are met. The best design was found by the 25 by 50 PSO at 88.5% efficient. And we can see generally the ones found by the particle swarm did perform slightly better than the ones found by the genetic algorithm. For the most case, it's not true in every case. For example, in the 10 by 10, the GA actually performed a little bit better, but in general, the PSO was able to find slightly more efficient designs. And we can observe the same effect in the second method for calculating efficiency, where we see that across all of these cases, the general trend is that the PSO performs slightly better than the GA due to its better searchability. And again, the best design overall out of all of these runs was found by the 25 by 50 PSO. So this next slide just shows an example of the convergence history or evolution history for both of these algorithms. And once again, I don't want to get too bogged down in the details of this. These are showing some examples. These are showing the 25 by 50 runs with a large punishment. On the left side, we have the PSO, and on the right side, we have the GA. One of the general trends that we can observe is that the PSO tends to look a bit messier than the genetic algorithm. We can see here in this top left is the shaft speed. Then we have the number of stator blades, the number of rotor blades, and this bottom right corner is the fitness value. And then the red stars in there represents the mean fitness value for the entire population at that generation. So we can observe that a lot more is happening. There's a lot more movement going on between all three design variables, which can especially be seen in observing the mean fitness value, how it fluctuates a lot more up and down rather than for the genetic algorithm, where everything pretty much stays constant after a certain amount of time. In a specific case, maybe after about 15 generations, there's no movement happening, which means that no search or no optimization is actually being conducted. And once again, we can see that in the fitness value. It reaches a constant value, and then after that, pretty much nothing happens other than this one spot where it actually decreases a bit. And same behavior can be seen in the second efficiency method for the total efficiency. Once again, we see that the particle swarm does exhibit a better searching ability in that it continues moving even after it has found the best point that it has. It continues to search around that space more so than the genetic algorithm, which in this case, maybe after about 20 generations, it just doesn't move at all. No optimization, no actual changes taking place. Trying to find my mouse. So some general trends that we can observe from the optimization behavior side is that the particle swarm runs did take longer to converge. It took longer for the particle swarm to settle out to a certain value. And in some cases, as was seen in the previous few slides, sometimes it didn't settle out to a single point at all. And this is due to once again, its superior searching ability. Even after it finds the best point, it continues to search globally and continues to search locally. whereas the genetic algorithm was observed to converge quicker in that all of the designs trended towards a common spot quicker than PSO, but it has a worse searchability, and it also exhibits that same tendency to lose its population diversity a lot quicker than the PSO did. The particle swarm generally yielded more efficient designs, though this wasn't always the case. This majority of the times, the particle swarm performs a few, maybe 1 or 2% better than the GA designs. Additionally, the GA was seen to be a bit more sensitive to the initial state due to its worse searchability. This slide is the best performing overall fan for the first method of calculating efficiency, the propulsive efficiency. And once again, on this left, we have a 3D render of it from AxSTREAM. It was found by the 25 by 50 PSO with a large penalty factor. As we can see, it meets the thrust constraint. That 11.4 kilonewtons is just on the low end of that minus 10% of the nominal thrust value. And it consumes less power than is available to it, meeting that constraint as well. It is, as expected to be, it is less propulsively efficient than the baseline because more work is having to be put into the flow, resulting in a higher velocity that's needed to meet that thrust constraint, hence why it is less propulsively efficient. But we can actually see that the total efficiency increased over the baseline design, even though this wasn't something that was explicitly trying to be optimized in this method of optimization. Another thing to note is that the only constraint that it doesn't meet is the total pressure ratio. It underperforms on that. And as we'll see with the next design, it does as well. So this is the next design. Once again, we have a 3D render of it generated within AxSTREAM. It also produces about that minus 10% of the nominal thrust value while consuming less power than we need. This design did consume a little bit more power and make a little bit more thrust than the previous design. And once again, as expected, it is a bit worse propulsively efficient than the baseline, but it does have a higher total efficiency. This is almost 2% higher than the baseline total efficiency of 89.9%. And once again, it does not meet the total pressure ratio that we require from it. This comes from the fact that the thrust constraint that I implemented in there is relatively large. The plus or minus 10% seems to be just a bit too large. Though I imagine if this were constrained to maybe plus or minus 5% or plus or minus 1%, that we would see that total pressure ratio rise to meet the 1.25 that's required from the steady state model. So that brings me to my next steps with these optimization studies. The first would be, yes, to investigate the stricter constraints. So rather than constraining the thrust to plus or minus 10%, maybe decrease that to plus or minus 5 or 1%, or perhaps even having the total pressure ratio as its own constraint as well. So the only two constraints I've considered in these past studies have been for the thrust and the power, but maybe the addition of pressure ratio constraint as well could benefit the design. Another thing I think would be worth looking into is having a dynamic penalty factor. So the penalty factors that I've applied in these runs have just been a flat static value for each constraint violated, but the dynamic penalty factor will actually change based on how extreme that constraint violation is. So maybe if the design is only a little bit off on the thrust, maybe the design is 12.5 kilonewtons out of 12.7 kilonewtons required, a smaller penalty factor could be applied. But if a design made only 5 kilonewtons, then a very large penalty factor could be applied to kind of more aggressively steer it towards the right direction. Another thing that is hugely worth looking into, and there's a lot of literature on, is what's called parameter tuning, where you adjust the factors that dictate how the algorithm as a whole performs. So for the particle swarm, this would be the particle inertia, which represents the how easy it is for the particle to change its velocity, how likely it is to move. Its personal influence coefficient, which dictates the influence that its own history has on its movement. Its social influence, also called the cognitive influence coefficient, which dictates the effect that its neighbor's movement have on its location, and as well as the neighborhood size. So maybe it only considers points that are very close to it, or maybe it considers points that are medium close to it, or maybe it considers every single point within the domain. It takes into account all of their movement. For the genetic algorithm, things that could be changed are the selection criteria. So what individuals are actually chosen to be able to reproduce to make the next generation of individuals. The crossover rate and mutation rate, which the crossover rate is how likely is it that genes will be crossed over from one parent to another and making the child. And the mutation rate is the likelihood that a random gene will be like randomly mutated from one generation to the next. This mutation rate particularly can be seen to affect the premature convergence, affect the loss in population diversity. By adding that randomness in there, you can help sort of agitate the evolution. And the last thing could be, it's not directly a parameter that influences it, but it's the concept called elitism, which basically says that the most efficient, the most fit individual, or maybe set of individuals are guaranteed to reproduce and move on to the next generation. And lastly, another huge research area of open questions are adaptive parameters. So each one of these parameters that I just mentioned could change its values over time as the run continues, as the generations go on. Maybe the particle inertia gets more and more. So it starts out being really easily moved, but as it reaches its end, it's harder to move. Things like that. So there's a lot that could go on with the optimization side. But as for the fan design side, I would say first we're looking into getting this integrated with the steady state model. So everything I've taken from the steady state model within my studies currently have been a one way. So I've just taken those parameters from the model and put them into all of my work, just as this is how it is, this is given, nothing will change, and there's no feedback in there. But adding a two-way communication between the steady state ease model and my optimization studies could be hugely beneficial in maybe investigating more things in our system. Additionally, I had mentioned that the baseline design for this study was intended to be the baseline for counter-rotating, and this is some of the work that I'm doing now. I'm investigating making that stage of stators into a counter-rotating stage of rotors and performing these same studies on it, putting it under these same constraints and same set of runs and sizes and lengths. The last thing I think could be worth looking into is adding more blade control for the optimizer. So my design variables in this study were just the shaft speed and the number of rotor and stator blades, but maybe adding in controls for the inlet angles, the outlet angles, the restagger angles, or the chord length of the blades. That could be something that's really worth looking into, especially for the counter rotating, as those are a lot more sensitive to the flow paths. And since AxSTREAM is pretty quick in its design, this would be a relatively easy thing to implement, even though there would be a lot more design variables and you'd have to hugely increase the design space. Because AxSTREAM performs the simulation so quickly, this wouldn't take as much time compared to doing the same study with a more traditional CFD study. So that's it for my webinar. That's all I have to present. I'd like to thank the NASA CLEAN ULI project. All of this work is a part of that project, and it's all being funded by the NASA project. I'd also like to thank Raytheon Technologies, particularly Scott and Dimitro. They've really been a huge help in my research and getting me introduced to AxSTREAM, set up with AxSTREAM, showing me things on how the software works and things I can do with it, as well as on the fan design side, sort of steering me in the right direction. So huge thanks to them. I'd also like to thank Softenway and AxSTREAM themselves, because, well, without the use of this software, I wouldn't be able to complete the study in a timely manner at all. And I'd also like to thank all of you. Thank you for your time, and thank you for attending. And now I'll open it up to any questions.